me know if the slides are not shared on your side of the screen or if it needs to be enlarged. So in this session, I will be covering a few topics and applications that can benefit from the techniques and methods available in deep learning. I'll start by reviewing a little bit of the basics of deep learning that will be beneficial for this discussion, and I will cover three applications: how to apply social distancing tracking, how to benefit from medical imaging diagnosis to diagnose the positive COVID-19 cases, and how to apply deep learning for drug discovery. And since there are a lot of materials in this aspect, I cannot cover all of the applications, but I will list the other applications that were not available to be covered in this context. So I'll start with a deep learning review, the techniques that will help us in this discussion. Briefly, I will go over GANs, deep reinforcement learning, graph convolution networks, and transformers. So GANs or generative adversarial networks, this is the adversarial training from game theory put together by Ian Goodfellow in the year 2015, and it benefits from training two neural networks in adversary game against each other or zero-sum game. The input to the generator is random noise, and then the output is generated images, text, videos, or audio waveforms. And then the discriminator is trying to figure out whether the input data is generated by the generator or actually is real data. So this pattern has been applied in many applications. It has been applied intensively in entertainment and in deepfakes, but it has, as we will see during this discussion, a lot of industrial and medical applications. The other technique that I would like to go through is deep reinforcement learning. And deep reinforcement learning originates from reinforcement learning itself, which is available for Atari games for a long time. But then with the boom of deep learning, deep reinforcement learning has benefited from the fact that you can build deeper networks and utilize convolution neural networks to extract features from scenes directly and then feed them into the neural network to figure out a decision over a action search space. So if the action search space is discrete, you go with Q learning or value function learning. And if it is continuous, you preferably go with the policy gradient learning. There are a lot of similarity from a philosophical point of view comes when you compare the deep reinforcement learning and the generative adversarial networks, and especially when you explore the technique actor critique algorithm, which is very similar to the generator discriminator pattern. And the deep reinforcement learning, we will see how it is applied in drug discovery, but it is mostly applied for drones, for autonomous driving, for robotics, and many other applications. It is very well known for defeating the world champion of AlphaGo. That is when they put together the value function learning and the policy gradient learning in a hybrid pattern, and that was by DeepMind a few years ago. The other technique that I will cover in passing is the graph convolution networks, very similar to recurrent neural networks, which works with sequence, whether it is time series or a text sequence. The graph convolution works with 3D molecular structures to extract features. However, the origins of this technique were put together to discover patterns in the social media database. With the boom of social media, Facebook, Twitter, etc., the nodes represented the users, and the connections between the nodes represented the interactions between the users. In the context of drug discovery, the nodes will represent atoms, and the links between the nodes will represent the bonds between the atoms. It takes a lot of art and science to design the graph convolution networks to extract the right features from the molecular structures and filter them with the right amount of neighborhood and distancing functions in order to capture enough information about the nodes and their neighbors. Next in this discussion, we'll talk about transformers, which have taken the world of natural language processing by storm, and they have been very successful in natural language processing and natural language understanding in what is known as zero-shot learning. And we can see here that transformers were first mentioned in the paper Attention is All You Need in 2017, when they have completely discarded the recurrence or the recurrent neural networks and replaced them with autoencoder with attention. And attention is very interesting because it is computationally efficient, as it does not have the recurrence overhead, and also it has shown extraordinary results on data sets for sequence modeling in natural language processing. We can see that the same techniques apply to the resulting graph embeddings, and we'll find that the graph embedding is very similar to zero-shot learning in that aspect, but with different objective, in which here we are trying to predict the properties of the chemical compounds, whether they are valid and feasible for drug discovery or not. So this covers the few ideas, the head points, the bullet points that we need from deep learning in order to understand the applications and their impact in recovering from the COVID-19 crisis. Before I go over the applications, I would like to make sure that there are no questions. Let me double check here. So nobody has asked any question. The chat is empty. Please, if you have any questions, just feel free to post them in the questions tab. If the voice is not clear or if the screen is not shared properly, please let me know. So back to our discussion, we started by reviewing the applications of deep learning in applying social distancing and lockdown restrictions. Here we can divide the tracking applications into a few categories. The one for epidemiological or viral model, in which you are trying to predict or forecast the pattern by which the virus propagates, and the other is by measuring the social distancing itself and whether it is applied or not. Of course, the big data technologies play a major role in this kind of tracking and surveillance systems, especially in countries like Hong Kong and South Korea, where they have shown extraordinary performance in applying the restrictions over a population of, in South Korea, for example, around 45 million. And the big data allowed them to capture the relations wherever there is an instance of COVID-19, they can quickly track the pathway of the patient and send the notifications to all the neighbors who might have passed over a circle of 1 mile, for example, around that area where he might have visited, so that they can be checked instantly, and the right precautions will be taken to prevent the more spread of the virus. So this kind of tracking at scale is very interesting because it actually merges the techniques of deep learning with big data. And we know from the free lunch theorem that deep learning requires a lot of data so that it can improve its performance. And this connection between big data and deep learning is very interesting and very intuitive. And it's kind of the cornerstone of the current technology, or the spearhead of the technological boom in that aspect. The image here is from one of the companies. This company has developed their face recognition system so that they can actually do recognition on masked faces. It is not a very new idea, because in object recognition we had the notion of applying deep learning and recognition on objects with occlusion, or objects that are partially visible, or objects with distortions. This example here has proven valid so that they can simply track the violators of the lockdown. It's kind of interesting with applications that help governments in that aspect. Diving a little bit deeper into the recurrent neural networks, here with a model SeerNet. SeerNet is based on the partial differential equation model, Seer epidemiology model, which is used to model the spread or the propagation of the virus and what kind of interventions can be taken to flatten the curve. So these models, they are based on partial differential equations, and meaning they are tracking the amount of change or the rate of change of the observable states with respect to time. The observable states or personas in this aspect are the infected people, the susceptible people, the exposed people, and finally the recovered people. So instead of having a hard-coded mathematical formula not taking into account other factors, the authors of SeerNet model have used both Google cell mobility data and other factors about the environment, the population, the weather, and so on, and fit them together to the SeerNet model, which is based on recurrent neural networks, so that it can forecast the number of cases and the number of recoveries at each time point in the future. So they have tried two different algorithms, one with a linear cell that is basically a multi-layer perceptron or neural network, and the other with a long-term, short-term memory cell, which is a pattern of recurrent neural networks that allows to capture the context of the time series and allows it to control the dependency, whether be it previous states from very long time or from very short time. And they have benchmarked the two models together. The innovation in this architecture is that they have put together another recurrent cell, which is SEER cell. SEER cell is kind of a cell that predicts the four observables of the equation using the same intuition behind recurrent neural networks, which is the use of Boolean operations like sigmoid and hyperbolic tangent to produce zeros and ones and weighted priorities. So this is one of the examples. Another example is here is measuring the actual distance between the tracked persons or people in pedestrian imagery or video footage from the streets. Let's have a distinction here between object tracking and object detection. Since object detection is concerned with analyzing one input image most of the time, but object tracking is concerned with analyzing over a sequence of frames of images that is a video. So it has this temporal dimension, not only the spatial dimension. And there are many ideas and algorithms in this area. And one of the famous data sets, if you'd like to play around, you can experiment on the X-Ford pedestrian dataset. So instead of applying the detection or tracking as per the green boxes, bounding boxes in the image on the top right corner of the slide, you actually have an approximation of the distance between the detected people so that you can measure, for example, if two people are close to each other within a distance of 2 meters, then you fire an alarm, send a push notification to the people themselves, or send alarm to a police officer to take required precautions to ensure social distancing. The architecture is very simple. Here you can see on the bottom right corner of the slide the architecture of the go-turn method for object tracking, which actually requires the previous frame applies a filter so that it can detect the object of interest, passes it through a convolution neural network to extract the relevant features, and then merges that with the features extracted from the search region of the current frame. This way, the model can decide through a fully connected layer or a fully dense layer the actual location of the object of interest or the area of interest in the current frame. So it always requires a few frames, past frames, and the current frame to be processed. That's why object tracking is kind of processing intensive and requires large computing power. And it's quite of a challenge to apply it on embedded devices or embedded systems or surveillance camera systems. That's why it's kind of a hot area of research to optimize and find the minimum viable system that can be deployed with the minimum computational power. Another technology which is very interesting because it is borrowed from the ideas of self-driving cars, drones, and robotics is the LiDAR or LiDAR. It's similar to the radar technology but using light sensors. The light signal is sent and it hits a target and then travels back to the broadcasting sensor, and the time it takes to travel is then measured and divided by 2 to calculate the distance. Imagine that you're having a lot of sensors that are based on this technology put together, and then what you get is point clouds that require a lot of pre-processing in order to figure out the 3D structures in the environment. One of the innovations in this area and the recent states of the art is LiDARnet. LiDARnet is put together by NVIDIA, and you can see the pattern here, even though it looks very complicated, but it is borrowed from the BEX-to-BEX architecture, which is a generative adversarial network method, very famous one of the methods used to convert images between two domains. For example, if you feed in a original image to BEX net, and then the output will be the semantic segmentation with object annotations for each object in the image. For example, a person, a tree, an obstacle, a road, a sideway, and so on. The other innovation in this architecture is that it takes into account two projections of the scene, an elevation view and a front view, and merges them together in order to figure out the features in the image and making a relevant segmentation. So compared to the previous slide in which we had the object tracking, this one is more like 3D sensing of the environment and usually goes in the literature by the name sensor fusing. A few data sets are referenced here, New Scenes and Kitty, if you'd like to play around with them. The second area of application is the diagnosis, in which we are trying to figure out whether a patient is positive or negative. And this one, we mainly covered two papers recently published. They are not the only published recent papers in that aspect, but they are kind of the eye-catching papers. The others are equally interesting. I will highlight a few points about each of them. COVID-net, based on convolutional neural networks for the processing of MRI scans and X-ray images. The other one is the COVID-CT dataset, which is a crowdsourced dataset of images if you'd like to test whether you can build a neural network to detect positive and negative COVID-19 imagery. A very interesting architecture. It's interesting because it was not designed by a human. It was actually figured by a neural architecture search algorithm, AutoML. So this network is designed by a machine, but you can see it's very similar to another architecture, which is called ResNet. And you can see here there are a lot of skip connections between the modules. And the pattern here is projection expansion, projection extension, or PEPX. It's a very fancy name for a simple idea, which is based on reducing the number of filters by using one-by-one convolutions. When I say the number of filters, for example, if you are working with RGB images, you have 3 filters for red, green, and blue. So in intermediate layers of neural networks, the feature maps extracted by convolutional blocks, they usually have a large number of filters, for example, 256. So in order to make feasible calculations in runtime, you apply one-by-one convolutions, reduce the number of filters, expand them again, and apply the convolution to extract the meaningful features, and then apply another projection extension pattern. This idea that allows the gradient descent method to figure out the relevant sparse features that are distinctive for the objective function. For example, if we are predicting whether the image is positive or negative, then it will extract the features that determine whether this image should belong to one class or the other. They have also crowdsourced a data set COVID-X, and it has an adequate number of samples which you can download if you go to the open source code repository on GitHub of COVIDNet and download COVID-X dataset. One of the oldest challenges on Kaggle is the platform for data science competitions, is the pneumonia detection challenge. So in the previous architecture, we had 3 output classes: COVID-19 negative, COVID-19 positive, and a third case, which is pneumonia due to bacterial or other viral infection. This is important since not all pneumonia cases that affect the respiratory system are due to the COVID-19 virus. So this competition about pneumonia detection, it has a data set for pneumonia, the image data set that you can play around with. One of the ideas that I find interesting is transfer learning. So you can apply transfer learning to reuse the patterns from different other image data sets, and then use the same weights and retrain the model with few number of data images, for example. Transfer learning is very useful in case if you don't have enough training data. Try to see the competition and available coding kernels if you'd like to have an idea. Finally, the COVID-CT dataset is again crowdsourcing the images by scraping them from preprints, and then it's using transfer learning once again by training a DenseNet, a variation of ResNet architecture, but with the residual blocks connected in much more dense way, that every block is connected to the following blocks. So this is an interesting variation of ResNet called DenseNet, and it was pre-trained, that is transfer learning, with the chest X-ray 14 dataset. Also, one of the datasets that includes images for the chest X-ray imaging, if you'd like to play around with, and the source code is available on GitHub as well. Finally, drug discovery, which is the kind of the cornerstone of fighting the pandemic. And let's see the potentials of deep learning in that aspect. The first idea, as you can guess here, is to design a new drug that is not existed before. But the most feasible and cost-efficient idea is actually repurpose an old drug and then reuse it with the COVID-19. For example, a drug that worked with other SARS-CoV-1, the first version of coronavirus, or the other one which worked with other respiratory system infections. This drug repurposing is more efficient in that sense. The idea of deep learning in drug discovery is by reducing the search space in the molecular combinations, so that you can generate the compounds, chemical compounds that are valid, that satisfy criteria, that is not toxic, that is high metabolism, and so on. And by reducing the search space, you can reduce the number of clinical trials that you need to perform, and that's consequently you reduce the time required to come up with a vaccine for COVID-19. One of the sources that I would like to reference here is the drug bank. You can find the white paper mentioning a lot of information about the recent work in that aspect. And you can see here the virus on the side, which has the protein envelopes in the pink color, and then the spikes. These spikes are actually the spikes used to penetrate the respiratory system, the lungs. And some ideas came that we might actually damage the spikes so that the virus is harmless. The protein RNA, the single-strand RNA virus COVID-19, it has around 29,000 genome signatures, which is a very large number compared to other mutations, and makes it kind of very challenging to combat in clinical applications. One of the very innovative architectures in the area of molecular biology or drug discovery is MolGAN, which is Molecular Generative Adversarial Network trained on QM9 chemical database. You can see it has ideas from generative adversarial networks with a generator and a discriminator to determine whether the generated compound is valid or fake. And it also merges it with the deep reinforcement learning by using a critique or a reward network. In this case, it is trying to maximize the properties of the chemical compound, that is solubility, the distribution in the organs, and exertion, metabolism, etc. So these combinations of ideas, it gives you the idea that the deep learning is kind of jigsaw puzzle. Once you learn the basics, you put them together in order to make modular applications and benefit from all these techniques together. Again, transfer learning can be used in the area of drug discovery by transferring the networks trained for natural language processing to the networks used for SMILES. SMILES is kind of a notation, a grammar for describing 3D molecular structures. And then by using transfer learning, you can use the pre-trained models in new applications with minimum retraining effort. So transfer learning is again one of the key cornerstones of modern deep learning. One of the very recent papers is deep drug repurposing, and it has 3 stages. And the idea here is that it tries to find the similar viruses or protein structures to the virus of question. And then it tries to find the similarity between the drugs proposed to those similar viral infections, and then apply autoencoder in stage 2 so that it can extract relevant features, and finally use that to do a prediction whether this old drug can really fit with this new virus. And this model was trained and validated with clinicaltrials.gov database, and it has actually proposed a few valid candidates for Alzheimer, the dementia, and a few other diseases to come with, available in the paper if you are interested in reading further. Because the time frame is limited and I would like to cover as many topics as possible, I have here miscellaneous applications that are interesting but did not fit into the 3 categories. You can see here on the image, I have a kind of a graph relation, and I search by chloroquine or chlorophene, and then it gives me all other viruses that are affected by this drug, for example, Ebola, SARS-CoV-1, and similar others. So this kind of data mining techniques and data visualizations are interesting to help decision makers arrive at better conclusions. On the other hand, there are the blood testing, because you know very well that testing for COVID-19 takes a lot of time, and a lot of innovation has been put together in area of fast discovery of the infection, and a few of them have been approved by the FDA in the United States, but a few others have not been approved yet. So these are a few other ideas that might be of interest to the audience in here. That was a quick landscape or bird's eye view of the deep learning potentials in fighting the COVID-19 SARS-CoV-2 virus or novel coronavirus. I hope that I have helped you have a quick idea what can be done, and I would be glad to receive your questions under the questions tab if you have any. Thank you very much. So we are always developing the methods and the ideas applied in the boot camp. So here Shwi Tank Yadav has asked a question: how many of these techniques will be covered in the full-time boot camp? So most of them will be covered, and since the boot camp is very generic in nature, we cover as many techniques and ideas as possible, from self-driving cars to medical applications to chatbots, to give you all the tools in your toolbox that will allow you to conquer applications in real life like this one. And this actually is a valid application of deep learning. There are a few others in power management, for example, when you are trying to predict power management patterns. All of these applications are a kind of the case studies we are trying to emphasize during the bootcamp, so that you are not only learning the mathematics of deep learning, but also powered with a powerful, very rich tool set that allows you to apply the techniques whenever in need in real life. I hope I have answered your question, Shui Tank. Please, if you have other questions, feel free to post them in the chatting. So if anybody else has got some questions, please feel free to send all your questions in the chat or in questions tab. All questions are welcome. So here, Vinay Kumar Ravi, can you discuss more on how natural language processing can be used on existing biomedical literature data to extract information related to genes, drugs, to COVID-19? So natural language processing is a very wide area of research. One of the ideas that you can apply to natural language processing in this aspect to extract information is to apply a simple search engine over the research papers on the archives or on other Google Scholar, and then use a term frequency inverse document frequency, which is a very simple algorithm if you're asking for simplicity. Or you can use other word embedding technique, starting from word to vec, fast text, Elmo, Glove, up to the more advanced ones like BERT, XLNet, and Turing NLG. All of these are word embedding techniques that can be used for sequence modeling. And then, having extracted the features using an autoencoder to encode the data, you can store them in Elasticsearch dataset. And from there, if you have a query and starting with a word, you can quickly, in a matter of a fraction of a second, come up with the most relevant papers or corpus in your data set that address the question in hand. For example, chloroquine, and then that will bring up all the encoding that is very similar in distance metrics, for example, Euclidean distance or Manhattan distance, etc. Whatever distance metric you are using, and then come up with a few recommendations in that aspect. One of the other techniques that can be used, but not on text corpus, on biomolecular structures for chemical compounds, is graph embedding, which is the analogy of word embeddings, but in the world of graph database. So I would recommend that you check word embeddings and their variations, and you'll find a lot of pre-trained models and available techniques that you can borrow in this example. And there are some applications I have come across that already address this problem, and by solving the problem using similar techniques like the ones I have just mentioned. Thank you, Vinay Kumar Ravi, for the question. I hope if anybody else have got questions. So you can see that COVID-19, here another question from Shanking Shu, and he's asking how to handle unbalanced data set properly, which is common in this approach. So this is actually one of the very common problems in the COVID-19 crisis, because actually not all the images detected or the blood tests collected are positive. You'll find that most of the time the dataset is imbalanced. So you can actually use data augmentation by generative modeling, or by using data augmentation by changing variations of rotation, shear, and so on. You can use downsampling by reducing the number of samples in the majority class, or you can use oversampling using one of the algorithms for oversampling, and then you can increase the number of images in the or blood samples in the minority class. These all techniques, they work by having the idea of neighborhoods, so that you can have one neighborhood, and then you know that if you have similar to k nearest neighbors, if you have a few collections or high density of samples in that area, then most likely if you want to generate a new sample in case of oversampling, then you can go a little bit distance around the existing images or objects, and this will provide you with the right kind of samples that you need to balance your data set. Generative modeling with generative adversarial networks is one of the best ways to augment medical imaging data sets, and a lot of papers that I have come across have actually solved this problem with generative adversarial networks in medical imaging. One of the techniques that I recommend to read a lot about, because actually in my own experience, generative adversarial networks and deep reinforcement learning are underexplored in the literature and in the curriculum by most data science academies. I hope I have answered your questions. Yes, most of the data sets in this discussion, or actually all of them, QM9 dataset, COVID-X dataset, and COVID-CT dataset, all of the dataset I've mentioned are public datasets that you can download and play around with, along with GitHub repositories for the code as well. Thank you, Krishna Amini. That was a question, whether the datasets are available for public use. Please, all questions are welcome. You can ask your questions in the chat tab. We have got 5 minutes more 5 minutes to go, if you'd like to ask a few more questions. So I think that's it. Thank you, Shutank Yadav, Vinay Kumar, Ravi, Shan King Zhu, and Krishna Amini. Thank you all for the questions you have asked. Please feel free to send your questions by email or on our page, or whatever medium you think you can reach us on. I would be glad to answer all your questions even after the webinar is complete. And then it will be available on our page if you'd like to go through the material once again. And in case you have not got all the points, you can read more about them in the reference papers. And you'll find a lot more papers than the ones we have mentioned, as the development in this area is very fast. Yes, very sure. I'll be sharing it with everybody who attended the seminar. Thank you. So Shanqiang Zhu was asking whether we can share the slides. Yes, very sure. We will be sharing the slides with all the attendants. Thank you very much for your question. So I encourage you to read more and explore the techniques and play around with the available code repositories. And if you have any questions, reach out to us anytime, anywhere, through any social medium, and we'll be glad to answer all your questions. That was Mustafa, and I hope that you have enjoyed this landscape overview of deep learning techniques that can be used for fighting the pandemic that's taking the world by surprise. Thank you, everybody. In case nobody have got more questions, we can end the webinar now. Thank you, Shwetank Yadav. Thank you very much. Okay, thank you and goodbye, and see you in a future webinar. Stay tuned on our page. Bye bye.